joining us. Dr. Schweitzer is the President and Chief Technology Officer of Schweitzer Engineering Laboratories. Dr. Schweitzer III is President and Chief Technology Officer of Schweitzer Engineering Laboratories. SEL, it's recognized as a pioneer in digital power protection. He's an IEEE Fellow and a member of the National Academy of Engineering. He's received multiple awards from universities, industry associations, including honorary doctorates and a 2012 medal in the power engineering, the highest award ever given by IEEE. Dr. Schweitzer in 2019 was inducted into the National Inventors Hall of Fame for his invention of the first digital protective relay, and he's written dozens of technical papers and holds more than 200 patents. He received his BA and master's degree in electrical engineering from Purdue and his doctorate from Washington State University. In 1982, he founded SEL to develop and manufacture digital protective relays and related products for services for electric power system. Dr. Schweitzer, we're glad to have you with us and enthusiastic about hearing your presentation and your slides. So, Dr. Schweitzer, I turn it over to you, and thank you so much for joining us.
Well, thank you, Sheila. Thank you, Will. Good morning to all of you from the Smoky West. When we're talking about carbon capture and finding ways to produce the energy that people need with less environmental impact, you only need to look out the window and see what a little lightning and natural causes have produced in terms of really environmental disaster with unhealthy air. So we're sort of double sequestered due to COVID and also due to smoke. So you walk your dog outside, you got a 2-pack-a-day habit these days. So I want to thank you again for the invitation and the opportunity to talk a little bit about advanced technologies and the capabilities that we're working on. I think the place to start is with something very, very fundamental. We like to go back to first principles like F equals ma, and you can't push on a rope. And we're all fortunate in the electric power industry to be delivering energy at the speed of light. Nobody else gets to deliver their commodity that fast. Some people think about how successful deliveries are quick from online retailers that may be able to deliver twice a day in some areas. But we're moving energy at 186,000 miles a second. That's 11 inches is only 1/1000th of a second. And you compare that speed, which what, 6 microseconds to go a whole mile. And you compare that, say, to a train pulling coal at 30 miles an hour, or line pack moving in pipelines at 3 miles an hour. And us electrical guys, we look at this pipeline and see it's a 3-phase power system, just like the electrical one over there. So this is an amazing thing that brings tremendous value. And Edison and Insull realized that, and they focused on how combining diverse intermittent loads would demand less generation. The idea was this, that the big buildings were going up in Chicago, and many people thought that there'd be a generator in the basement of every building, like Marshall Fields would have his, Montgomery Ward's theirs, and Carson's, and so forth, and that these various generators would be right next to the furnaces of these buildings. And Edison and Insull realized that if you did that, those generators would be idle at night when the stores are closed, and the energy would be unavailable to parking garages and other makers, other businesses. So when you pull all that together through a transmission and distribution systems, you combine these diverse and intermittent loads, because you and I turn on the power to different loads at different times and in different places, whether at home or work and in our businesses. So the whole idea was there was tremendous amounts of capital to be saved, and much lower rates could be offered to customers. I recall reading in Insel's writings that it's about a 6-to-1 ratio, that it would take 6 times as much generation if everybody had their own separate sources in their basement and had to rely on those without the interconnections. So we've benefited from that thinking for 100 years. And these days, when we are working so hard to fully integrate photovoltaic and wind sources, it's apparent that these diverse sources and their intermittency have a similar characteristic to the loads that I just talked about. So when, by moving energy at the speed of light, we can combine these diverse intermittent sources over broad areas, we can serve more load and make them more dependable. So instead of them being intermittent, they start being dependable. And the more we make them dependable, the greater value they have, so that the public service companies can provide us the energy when we need at the flick of a switch and the speed of light. Two important concepts: the age-old one of combining the diverse intermittent loads, and then also today adding into that the combining diverse intermittent sources to be more valuable. So what I want to talk about technology wise was, of course, we're in the business of protecting electric power systems. And what that generally means is, well, when something does go wrong in an electric power system, being able to trip circuit breakers fast and correctly so as to there's the least amount of damage, the shortest interruptions, and the greatest amount of safety. So the faster we can do that, the more stable the systems are. We can transmit more energy through the same transmission systems. There's less damage from the electrical faults, less cascading of problems, less stress from overloading equipment, and also less stress due to faults within transformers and generators, and less shorter and less voltage sags keep customers happier in their critical loads. So there's a lot of motivation here. And in fact, if you think about it for a minute, we're moving energy at the speed of light. We need to be protecting power systems at the speed of light. So let's go back here a second to another fundamental thing and ask what really happens when I turn on a light. So if I go over there to the light switch in my office and turn it on, a traveling wave propagates away from that switch at 1 nanosecond. It goes 11 inches, and in 6 microseconds later, it's a mile away. That traveling wave, it reaches a generator. The current increases in its stator. The torque increases, taking a little bit of energy from the rotor, slowing it down. And that kinetic energy of the rotor is converted to electric energy, traveling back to me. And the waves travel back and forth, establishing the new equilibrium. And if I turn down a 100-watt light, that all happens so fast we don't even know it. And then eventually the governor notices that rotor's a little slow and opens the prime mover enough to add just the right amount of energy to the rotor. So this is an important thing to think about, because look, Ma, no computers, no internet, no communications other than the act of me turning a switch on and off. And all this happens so very fast that we don't even think about it, and we take it for granted. I want to show you a waveform here of some currents during an electrical fault. And let's look at the time scale at the bottom. It's measured here in milliseconds. And today we like to talk about milliseconds, microseconds, and nanoseconds. And we seldom talk about cycles anymore. So we can see here that there's a pre-fault current, and then an electrical fault occurred, and the fault current began to flow at a much higher value. the traditional ways of protecting power systems looked at this sort of cycle by cycle at about a 1 cycle response time or slower. So then we have been very successfully applying the traveling wave principles, and we zoom in on just that. Just the transients that I talked about, like travel between your light switch and the sources. So let's take a look at how we can use that and how well it works. So we've very successfully pioneered what we call time domain protection, moving away from measuring magnitudes and phases of sine waves. And I don't really care if they're sine waves, square waves, or DC, that when we move to the time domain, we can make things very, very fast, very accurate fault locating, very, very secure as well. So here's an interconnection between Mexico and Guatemala. There's about an 18-mile line. I think it's 230 kV from Los Brillantes to Palo Gordo. And this line has some traveling wave protection equipment on it that SEL developed. And it trips in 1 millisecond, not 1 cycle, 1 millisecond. Let's take a look at this. You can see the pre-fall load currents are quite small. And so the intertie was lightly loaded, and then a fault occurred on phase C. You can also notice a fair amount of current transformer saturation that can affect traditional protection. But when we zoom in on the first millisecond, we will find just the information that we need to make a tripping decision in just 1 millisecond. Let's take a closer look at the traveling waves of current. We've amplified the scale here, and we are sampling the currents and voltages 1,000,000 times a second to 18 bits of resolution. These are unheard of levels just as recently as a couple of years ago. So you could see that the traveling waves reach the two substations at slightly different times, measured really in microseconds. This is 200 microseconds now, so maybe they got to the two ends of the line only about maybe 30 microseconds apart. So if the fault had been right in the middle of that 18-mile line, it would have reached the two ends at exactly the same time, and those peaks would have overlapped perfectly. So you can even tell here that the fault was a little closer to Palo Gordo than Los Brillantes. So anyhow, we use this information. These are the same polarity, meaning they're both going up, not one up, one down. So, and some other things in order to make a trip decision. We really have a real good answer out here after about 400 microseconds, and we're able to securely, dependably trip in just over a millisecond. And that's the traveling wave differential element. And in a first product that we developed with these principles, that all the operating times were way sub-cycle, a quarter of a cycle, an eighth of a cycle, a 16th of a cycle, and less. So this technology is like moving from a car to a jet. So we've combined that time domain technology, this very fast stuff, with advanced Phasor-based functions too, to provide complete protection schemes. When you think that not only are we able to trip circuit breakers reliably, accurately, in a millisecond instead of 16 or 32 milliseconds, this really makes a big difference in safety and stability. There's another effect that our friends who make circuit breakers now realize that they have to speed up their game. They're already in the process of doing that. Many of the things that they are doing to make DC circuit breakers will impact in coming years the speed of protection. So a breaker today maybe 2 cycles, and now what is this, 2.01 cycles the trip? The relay time is really down to nothing. That's a transmission. I want to talk about also speeding up the game on distribution. Here we have a portion of a distribution system, and here's a recloser protecting a feeder, and there's a couple of branches here that are protected by fuses. And we got an age-old problem here. When the traditional protection is used, where you try to coordinate these fuses with the relays. So what you'd want is if you have a fault on, say, this fuse lateral, well, the relay doesn't know where it is, so the time coordination principle is to wait to see if that fuse is going to blow. Now, the last thing you want to be doing if you have a fault on a power system is waiting around to see what happens. That's like bad idea number 106. So today you do not need to wait for a fuse. So how do you sort it out if there is a fuse or there isn't? Well, these little fault transmitters, which are a little bit bigger than a coffee cup, clamp onto the conductor. You install it with a hot stick. There's no batteries in it. It takes its power from the power line, from the current, and fires up a little transmitter that sends out an encoded message whenever fault current goes through here. So you put these out at various points like the blue dots show, and now if you get a signal from this main line fault transmitter back here to the relay, guess what? You know you better not wait. There's nothing to wait for. On the other hand, if you get a signal from this one, you know that the scheme is to wait for a fuse. This is the idea of shaving hundreds of milliseconds off of the durations of faults. Here's a different example in some wind farms in Brazil. There was 9 wind farms that were set up like this. Here's a collector that brings the energy together from the wind farms through motor-operated disconnect switches. And the original design of this system, the engineers used one protective relay to cover the collector. Yeah, so a fault anywhere out here would trip the recloser used as a breaker right there. And then maintenance folks would have to go out and patrol and see where the fault was, operate one of these motor operated disconnects to isolate the faulted part, and then come back here and turn the wind farm back on. So they got tired of doing that. It was expensive to be losing the very energy that the wind farm was built to produce, clean green energy at that. The 9 farms was a major challenge. So one thing they considered was putting in reclosers and relays at all these points, and the price tag for that would have been $2 million just for 9 wind farms. So with economics, that was out of the question. So they realized they could use these fault transmitters. So when a fault did occur, they could know right away on which of the branches the fault had occurred. The relay goes ahead and does trip the whole farm, but then they know which of these motor operated disconnects to automatically open and get the scheme back. So this saved $2 million. In fact, instead of spending over $2 million, they spent $80,000 on it. One of the fun things about it, there was no primary construction work. It was all just secondary, hanging the fault transmitters in place and setting up the receiver with the relay. Last thing I want to touch on is cybersecurity and the nature of everybody's so enticed by the convenience of and the speed of the communications by Ethernet and internet that we really want to use it. And up until very recently, you could not safely use Ethernet in electric power system applications for several major reasons. One, it's non-deterministic. You could not tell what the delays are, what the routings are through the network. Second one is the cyber risks that oftentimes the bad guys know the network's better than the good guys. And the third one is when something happens in a network that the network takes a long, long time to reconfigure itself, heal, and be back up and communicating. That's the last thing you want to have happen if there's a electrical fault. So here's a little example. We went out to solve this problem, and we've been asking the question: what is inherently safe cyber? One of the things we did is we picked up on some software-defined network ideas and significantly advanced them in their application to electric power systems. So here's a relay that needs to be talking to an RTAC or a RTU in a substation, and here's an intervening network. And up to the one side, this orange thing is a software-defined network server. So what happens is you get into the server connects to these devices, and you tell these software-defined network switches what they should do. So if you want the white line to be the primary path and the green line to be the secondary and the yellow one to be the tertiary, you program that here. All the switches know that. Even if they lose their control power, they come back on. When there's disturbances, the changeover times is rapid fast, sub-millisecond time. Another thing you do is you tell these switches only what kind of data shall be transmitted back and forth, which is a tremendous cyber advantage. And now one more thing it does is that these switches will tell you if somebody is trying to move some data through them that doesn't belong. So now let's take a look at how that would work. If you move lose the middle connection, the data goes through the green path. You lose the green one, it goes through the secondary path, and it's just that simple. So we finally can have safe cyber today. When our guys invented the SEL software-defined network technology, I was finally okay with using Ethernet technology in substations. It's dependable, cyber secure, heals fast. I'd like to keep in mind, though, that power systems have run fine without any cyber for 100 years. So why are we putting this risk into place? And a risk that we can safely mitigate today? Well, we know it adds safety, reliability, and economy to the power systems. And we now today can build core and edge systems that perform seamlessly with practical cybersecurity. And many of these devices that we develop have features in them to detect the signs of a cyber attack and do it fast. So bottom line here is we can and do build inherently cyber safe solutions today.
Thank you, Dr. Schweitzer. We're running a little tight on time, and we do have questions for you. So wanted to interject that, and really appreciate your remarkable presentation. But we're very short on time. If you care to wrap up.
I would. Thank you very much for the reminder. So we're busy inventing the future. We've made a big shift of thinking to the time domain. And we ask ourselves basic questions like how simple can we make a relay? And what are the roots of cyber insecurity? And all the time we're appreciating this wonder of moving energy at the speed of light and contributing to it, and hopefully in the process satisfying our customers as well. Thank you very much. I have my email address and personal cell phone telephone number on this slide, and would be happy to share information or answer any questions, not only at this moment, but later by either of these methods. Again, thank you very much.
And thank you, Dr. Schweitzer. Al, I know you have questions teed up. Could you let them be shared with Dr. Schweitzer now?
Yeah, definitely. Here, one question is, given your comments about the benefits of diversifying power sources, how would you assess the trend towards microgrids, community solar, and distributed energy? Aren't there benefits for resilience from such resources and the benefit of avoiding hard-to-build new grid additions? To what extent should we encourage distributed resources, even though they may be more costly than wholesale power generation and transmission?
many of the renewables are inherently distributed. Frankly, the most renewable energy storage means is often located far away from the renewables themselves, that being the water behind a dam and hydroelectric facilities. So we're already dealing with distributed resources. And frankly, it's not much different than dealing with different loads, distributed loads. So it's something that is, when we go back to the first principles, that is quite comfortable to us as an industry and as a company. Here, let me give an example. That we're so used to talking about distribution feeders. So what is that? That's maybe a three-phase circuit at 35 kV up on some wood poles. And then we start talking about wind farm collectors. So what's the difference between a feeder and a collector? Is just whether it's distributing energy to users or picking it up from distributed resources. It's the direction of the power flow, something that's very easy for us to handle and control and protection. So it's a very natural thing. The challenge is there is a change in practices. It used to be we would look at a feeder as power going from the substation to your and my homes and businesses, and in one direction. And now, when we start thinking about energy sources, be they storage or generation, being commingled with those loads, it turns these feeders into buses. They're no longer neither a feeder nor a collector. They're buses, and we need to know how to control and protect those, and we do.
Thank you so much, Dr. Schweitzer. And I know there are a number of other questions that we will get to you, and hopefully we may be able to send out a message or emails regarding them when we have the opportunity, and assuming you have the availability of time to answer them. Thank you so much, Dr. Schweitzer. Fascinating presentation.
Thank you. It's my pleasure.